So my name is Sylvain Cros. I'm a researcher at Laboratoire, météorologie, dynamique, École, polytechnique, mainly in solar power forecasting techniques. So you probably know that photovoltaic power instant value depends on many things, on several things. The first one is the PV panel characteristic. If your PV panel is big, you will produce more power. If it is little, you will produce less power. But it depends also on solar irradiance reaching the PV panel. It's the most important things. And never forget that PV production depends also on temperature, especially panel backside temperature, which depends on air temperature and also on wind and also on solar irradiance on the panel. Because when there is sun, the panel is getting hotter. And when the panel is too hot, its production is a little bit less. But the most important thing to know is PV power production is variable. If someone wants to say intermittent, I would say no, it's variable. It's intermittent at the scale of a night and day. But as you see in the curve, during a day, it's not intermittent, it's variable. You can see here on the three curves, the three causes of variability. The blue curve is the PV the global horizontal irradiance at the top of the atmosphere. At the top of the atmosphere, the irradiance is very high, so maybe we should put PV panel at the top of the atmosphere. Elon Musk will say yes, but no, because we are not living there. And then under a clear sky, at the ground level, but under a clear sky, you can see the red curve. This is the PV production under a clear sky. This production can change from day to day according to the ratio of humidity and aerosol. If you have a lot of aerosol, there is less production, there is less irradiance. As you can see, on the 23 February, the clear sky production is smaller than on the other day. But if you see the green, yes, you see the green curve, there is less irradiance because this is the real measured irradiance in Palaiseau when there is clouds. So when there is clouds, the shape is not smooth at all. And this day, for example, the irradiance is very, very smaller compared to the other day. So three causes: solar cross, cloud passing, and PV panel temperature, which is easily predictable, and it has a minor influence. So cloud cover is the main technical challenge for PV forecast, and we will talk about mainly cloud cover these following minutes. This is an example of a satellite images in the visible channel. There is a post-processing to enhance only the clouds. And you can see on this day, there is many different cloud motion. You can maybe guess that there is a fog between Paris and Orléans, which is disappearing during the afternoon. It's a fog, or maybe it's low stratus. We don't know. It's satellite image. It's not so precise. But what is important is there is several motion, and it's very difficult to study this motion and to forecast it. Because it's a stochastic phenomenon, PV power has a limited predictability. By theory, we will never have a perfect forecast because cloud motion are stochastic at this scale. So, why PV power is forecasting is important? It's important for several applications which are calling different geographic scales. The first thing forecasting is useful is sizing a PV farm project. This is not really forecast. This is climatology. we need people who are sizing PV farm. People who want to have a PV farm, wants to know what will be the production during the next 10, 20 years. So the forecast method is very simple. We take the time series of the last 10, 20 years, and we assume it will be the same on the next 10, 20 years. And so it is an easy forecast. So, and then we can use this time series. If this is specific, yes?
You say it is climatology, so do you account for climate change?
Not for this scale, actually, for solar energy. But 20 years ago, we did not account for this scale. Now, from today to the next 10 years, the climate change is not really, has not a significant impact on solar irradiance, on surface solar irradiance. If we are on more 30 or 40 years, yes, we have to take into account. But the modeling of solar irradiance climatology is still quite difficult because it's a good subject, and we will not do it today, but it's a good subject. But when temperature increase, the cloud cover might increase too because of evaporation. So for day-ahead needs, the grid operators have to manage their operational reserve for utility and grid operators, and also for trading. The most useful forecasts are day-ahead for the next day, and this user needs hourly time series of the next 24 or 48 hours. Intraday forecast, there is a need for intraday forecast during the same day, also for trading, for intraday trading, but also for microgrid management, with microgrid, with storage, with battery, and how to study the flexibility, how to define the best flexibility to increase the self-consumption, for example. So in that case, this user needs sub-hourly time series of PV power during the next hour. And the last case is intra-hour. Intra-hour is very short term. This is namely in the next 30 minutes. To start up genset or gas power for microwave or non-interconnected area, it is important to know the PV power in the next 10, 20, 30 minutes. And so this is a very short time horizon and very stock techniques for this. I just conclude this slide by saying that not all forecast benefits used are today identified or nor the benefits assessed. Maybe we can meet a new needs of forecast, and we can identify a new KPI on good or bad forecast. It depends on the new application which can come in the next years. So I defined the time horizon by the needs. Now I will show you the techniques according to this time horizon, to this scale. For very short term, we can use just PV production measurement or irradiance measurement. I don't know why my picture is black. It was a pyranometers, something you don't see every day. So it looks like a flying saucer, but like this. But it's something to measure the irradiance from the ground. So for very short term, we can use measurement and also all sky imager. We'll develop on that. Then for intermediate scale, for intraday scale, the forecast based on geostationary meteorological satellite images are very suitable and more efficient than NWP forecast. And for after 6 hours or day-ahead forecast, the classic NWP model are still the best solution to get day-ahead forecast. This presentation is more focused on intraday forecast, so more on camera and satellite, but we will have a few words on NWP, on how to improve it for these needs. So now let's go into the intra-hour forecasting. So the best forecast method at 1 or 2 minute time horizon is the persistence. If you want to know what will be the irradiance in 1 minute, it will be roughly the same as before. But for 2, 3, 5 minutes, persistence is not good. So the best tool we have for this forecast is the time series modeling. You need to collect time series of measurement. Measurement can be, this is pyranometer. You have it on the left. Pyranometer from CIRTA at Polytechnique. You can collect historical measurements of irradiance or PV power. You can measure, you can have measurement of PV power if you put an instrument below your PV panel, for example. And it's better if you can have your measurement in real time. It's not the case on every people. Many industrial, when we ask him, do you have a real-time measurement, they say, no, why, it was useful? No, I didn't know. Okay, so it's not available everywhere. But once you have good historical measurement on real-time measurement, you can use auto-regression algorithm. You can use more advanced machine learning techniques as ANN, random forest, gradient boosting, to forecast the PV power production in the next minute according to the past data. For further time horizon, up to 20 minutes, the whole sky imager is an interesting technique. There was many research on all sky. There is still many research on sky imagers since the year 2010. It's very difficult to get accurate forecasts from this tool, but the fact that we can see the coming clouds is very important. So at this moment, there is not a best manner than this to forecast up to 20 minutes. To understand the main principle, so we put a camera on the ground and we are looking at the sky on an hemispheric view, like you see here. And then for the video is normally easy to understand once you understood. We assume that the cloud trajectory are very linear. There is only one direction at each second, at each image. For each direction, a sort of scale, blue scale is drawn here, and then we can guess from which angle and in how many minutes or seconds the cloud will occult the sun. And the result is the curve below. The forecast is the red dashed line, which is here, and the reality is the gray area. So sometimes there is a good fit here, it's a good fit. Sometimes there is a not so good fit. So the forecast is not so good. So this principle has been used is still used, is still operationally used. It has been modelized since a while, since 10 years now. And to obtain these results, there is also a lot of work to make good image processing from the camera, and several cameras have been available on the market. The conclusion of this last year is the cheapest camera meet more success, like the Mobotics, for example. Okay. Okay. Okay, so, and then some companies try the infrared camera to see, oh yes, it works. To have more information on the contrast between clouds and the sky. This is the very original model to get an image from the sky. And now, so the Mobotics we have here are very cheap, and these cameras are coming from security purpose. Okay. So now the last work concerning the sky camera are deeply inside the deep learning model. So no more scale, no more blue scale seeing where the clouds are coming. Now we put images into a big box and we hope that the result is better. The result seems to be better today. So this is a neural network architecture. I will not comment them. I trust Palaiseau, is a good guy who did that. But so, And of course, the constraint is it's important to get a large training data set. So we need to have long time series of cameras seeing the sky. But the last finding was interesting. During his thesis, the thesis of Quentin Paletta, his main finding was that artificial intelligence needs to be helped. It's intelligent, but it needs to be helped. And if we put a raw image into a deep learning scheme, the results are not the best. Raw image. When we put a raw image, you get the brown stick here, which is the lowest forecast skill. If you focus on the area just around the sun, it helps the deep learning method to really concentrate on the fact that there will be less sun when a cloud is coming in front of the sun. It's easy for us, but for deep learning, we have to help here. And the most surprising thing is the polar coordinate. This is the same image, but with totally different projection. And the left side of the image is the circumsolar area, but it has been totally déplié. And with this kind of image, the results for forecast skill are the best, because the convolutional neural network have better view of what's going on with clouds on sun with such images. So this is the main finding: is we need to help neural networks. Yes. Oh yes, it's a big work. I'm not sure. I think it's totally conventional, or maybe it's ruled with solar crosses on the place. I think the idea is to get the longest time of the sun, of the apparent sun. But I can check that. And one camera is good, but several cameras are better. So there is a big project with DLR in Germany, who installed many cameras in the north of Germany to get a detailed forecast at regional scale. And some results start to be found now. And they try to have a large cloud map at very high resolution, and then apply such algorithm to get the PV power forecast. And another project, which is led by Paletta, is to make the survey of open sources sky image dataset in order to train deep learning algorithm. Because there is research who said that if you take a sky imager, for example, in Australia, and you want to train an algorithm applied in California, there is some, you can have some benefits. It's not totally stupid to do that. But it's better to have, of course, a similar climate, and it's better to have a variety of sky image dataset to train your algorithms. So now we're going into satellite images. So I'm working on it, so I know a little bit better. A few words about geostationary meteorological satellite. This is the satellite you might know if you see the weather news on TV. So these satellites are in orbit from the year 70s to enhance the forecast. What we should know about this is this satellite producing one image of the same place every 10 or 15 minutes, which is not the case of a low orbit satellite, which is totally useless for solar forecast. The satellite has a very high altitude, but because of that, we can see the cloud cover on about 1/3 of the Earth's surface. And with 5 satellites, we can cover all the world. And here, this is an example of 6 satellites from American, European, Chinese, and Japanese. We can cover all the world except polar area. Polar area are not really visible from such a satellite. And this satellite has the good channels to observe cloud properties. So you can see an example over France. Over France, the resolution is about 2 to 1.2 kilometers, which is quite nice for a satellite located at 35,000 kilometers. And we can, it's easy, we can easily get now the cloud property and distinguish a cloud type. Here you have a list of cloud type, which are here. For example, on this day. Here you have a cloud altitude. The blue are low, the other are high. And you have here the equivalent in terms of cloud index. Cloud index is a normalized index to which give a kind of cloud optical thickness, a kind of the power of cloud to attenuate the irradiance between the clear sky irradiance and the surface irradiance. Once you have this cloud index, you can play with them. I mean, you can apply optical flow analysis on images, and you can guess what will be the next images. So here, we compute with 2 images. We compute with optical flow the cloud motion vector. I don't know if you see there is green arrows. There is green vectors on this image, and this image doesn't have vector normally. We can better see on the control screen. Here is not obvious. So we have a field of vector, and when we applied this field of vector on the last image, we can extrapolate the cloud motion, and then we can guess what will be the next images. In this example, this is a good example. This is a very favorable example. We can see this cloud coming from Normandy above Paris. And this was the observation, and the forecast from 11 give us this time series, which is realistic, very realistic at the beginning, and then the shape is not is a little bit different. And in terms of results for this time, the red curve is NWP, is Météo France. Météo France forecast a little diminution of clouds, but as I told you, NWP are not very made to do very short-term forecast. So, but they detect a decrease of irradiance, but our forecast is the yellow curve, and the black is the observation. With satellite forecast, we could really catch this motion. We have a little mistake here, but we have the quite a good motion. And so on this kind of forecast has a reputation to be better than NWP up to 4 or 6 hours, depending on the weather situation. The advantage of this forecast is the high refresh frequency. Each time a new satellite image is coming, we can do a new forecast. So we can do a new forecast every 15 minutes. We don't need hardware unless to calibrate the measurement. It's good, but operationally no. And this is we can implement it worldwide. The technique to compute cloud motion, there was 2 main. There was a block matching versus optical flow. Now optical flow is becoming more and more popular because it gives a very smooth vector, but the performance of the 2 techniques is very equivalent. Optical flow is just easy to implement. And this kind of method is now very well known, but it's still used for baseline for new AI-based method. This is a comparison between actually optical flow and the block matching. So if I'm not wrong, the only block matching we have is the yellow curve, which gives a larger error than the rest, and other techniques of optical flow are very equivalent. This is the relative RMS deviation of forecast according to a time horizon. So you can see this progression. the error increases strongly and then is stabilized according to forecast horizon. This is the comparison between different methods are very rare. These people are coming from Uruguay and they test this forecast on some point of Uruguay using the American satellite, but they took methodology from state of the art. So beside the CMV approach, there was some attempt a few years to inject some machine learning inside this. So first attempt was to use a cloud motion vector, sorry for the between, and to mix that with spatiotemporal autoregression. It permits to focus, it permits to use statistical information helped with CMV. Because the cloud motion vector is good, you can do extrapolation, but it works only for cloud with horizontal motion. If a cloud is appearing and disappearing, the previous method could not see it. This method can catch some more with statistical purpose, statistical feature. This method gave better results than the classic CMV, but after a time horizon of 2 hours, the results was not satisfactory. Another approach is the probabilistic CMV, which has been developed at Mines Paris, in collaboration with Mines Paris. The idea is to attribute a Gaussian curve to every cloud motion vector, and then to deduce not the future, but different future here. And then we can have same method, but instead to have a deterministic results, we can have probabilistic results, just by assuming that a cloud motion has a Gaussian behavior. And then it gives probabilistic forecasts, which can be more useful for some applications, such as the trading. So now, as you know, we are in the time of deep learning. So many researchers are trying deep learning for this kind of method. First noticeable work was made in Météo France in 2020 by using a convolutional neural network. This is a famous one if you are in the CNN field. This is a UNet. UNet has been made for segmentation, for spatial segmentation, but it has been used to get a forecast. It has been used to use a temporal aspect. So there is some results with a binary cloud forecast. Unfortunately, this result has not been compared with the previous method, so there is no full comparison available. Other works combine this with recurrent neural network, and it gives some strange names like this to a mixing of convolutional and LSTM, a mixing of GRU, LSTM, and convolutional. Same thing. It gives interesting results, but there is not a lot of robust comparison between a CFB-based method. Generative models is a new approach to overcome a problem. With the CNN, there was a problem. Every forecast was a little bit blurry. Every next image was blurry. So the generative is supposed to build a realistic cloud shape. So there is a recent work on it to do a forecast generation. The drawback of generative model is that there is a big computation time, and it's not easy to reproduce it, because the hyperparameters tuning is very complex in such approach. So this is very new research. This is the beginning. It looks promising, but there are still difficulties to implement such method. And to do solar power forecast, we can get inspiration for similar fields in deep learning. For example, meteorologists did rain forecast using generative adversarial networks. So the GANs has been made to make a deep fake. Yeah, but now we used to do not deep fake, but forecast, forecast of some gridded parameters. So this is rain forecast from radar images, and we work to apply these techniques on satellite images. Another approach, another parameterizing approach is the physical informed neural networks, is how to give physics equation into a deep learning model. I will just say that, and there is more complex work behind, but it's just to add physics in deep learning model. The vision transformers, this is transformers which applied on images can bring many things, but we don't know yet what we can do with that. And of course, the new weather models made by big companies like NVIDIA, Google, and Huawei, donc Forecastnet, GraphCast, and Pangu Weather, give noticeable results for temperature, humidity, wind, but nothing has been tested yet for solar energy or accurate cloud cover. So a few words about day-ahead forecasting. It was not the focus on my presentation, but for day-ahead forecast, we cannot do better than using an NWP. This is the method used by a researcher on solar energy, is to do a downscaling of a GFS model. GFS model has a big advantage, it's free. And if you put output of GFS into WRF model, you can get reasonable spatial and time resolution for solar energy purpose. And of course, you can correct the observation with, you can correct the output with observation to reduce the bias. One thing to note is most of NWP tend to underestimate the cloud, and so to overestimate the irradiance. This is the main thing we have to reproach to NWP. There is an attempt to to increase the NWP forecast, especially for short horizon, by doing data assimilation of cloud product. This work, this thesis has been made, and some promising results has been found in Réunion Islands, especially. And just a few words about ensemble forecast, but Riwal yesterday told about that better than me. For solar energy purpose, for GHI forecast, it's a big benefit if we use ensemble forecast. We have really better results, and we have a probabilistic forecast. Some works has been made 5 years ago on analog forecast. It gives good results on very difficult situations, such as Réunion Island. Réunion Island is a French overseas territory in a tropical area, and in tropical area, the weather modeling is difficult. It changes quickly, and the clouds are coming very quickly. And so, analog forecast is to find correlation between variables which are not especially linked to irradiance, namely wind, humidity, diagonal circle of clouds. And the idea was, if a morning we have this humidity, this wind speed, this temperature, and this kind of clouds, then we have a probability to get this situation on the afternoon. It's an analogic aspect. This has been tested in Palaiseau with arpège, and we had honest results on a 2 years data set, but nothing very significant compared to arpège Météo France model. So it's the end for the moment for the forecast techniques. Now I will show you some application for intraday forecast, for very short-term forecast, on how we use it. This is the original, this is the most old things, the most old application we use forecast is PV power trading. So this is a drawing I made a few years ago to make understand how works the power trading. So maybe we had a presentation on this week, I don't know. But power trading is a meeting between sellers of electricity and buyers of electricity. There is a base block called future, which is programmed many months in advance. When there is a peak block, which is programmed usually at the beginning of the week. So this gray rectangle, oops, I spoiled. So this gray rectangle, there is nothing much to say about it. It's programmed from long time. But the red sticks is the production on spot market, where we are in a very short-term scale. And the problem of trading is undersupply and oversupply. Here, the black line is the load consumption, is the user electricity consumption. And on the left side, there is a case of undersupply. And this is a problem because at the time when electricity is distributed, the supplier of electricity has to buy electricity at a very high price with RTO in France. And RTO sell it very expensive. No? Not so expensive? Sorry? We don't sell it. No, but you balance the system, so you produce the penalty. You assess the penalty. Okay, thank you for this precision. And if there is another supply, then the producer has to sell it, but at a low price, and not an interesting price. So the forecasts are very necessary to avoid such problem. So there is a forecast of consumption. It's another issue. It's a big issue. It's not my topic, but it's also a big issue. And it has to meet the forecast of the production in red. So if you have a good forecast, normally you don't have so big penalties. And RTE can balance the system. Another application, which is quite new, of short-term forecast is the optimization of hybrid off-grid systems. On the left, this is a site very far from everywhere. Typically, it's a mine in the desert. Oui. Okay. Okay. So it's an engine which dig on the earth to do mine, which is supplied by PV panel, but also by diesel genset, which are dirty. So, but the idea is if we don't have forecast, the system is simple. If we don't have forecast, when there is sun, we use the PV panel. When there is no sun, we start the genset. The problem is the genset is like they are very long to start. So if we have no forecast, there is a spinning reserve of a genset. The genset are switched on day and night. Just in case we need it, we just have to accelerate the engine. But if we switch off, it takes 10-30 minutes to switch them on. With a forecast, if the forecast says there will be sun during 3 hours, then we can switch off the genset. And if clouds are coming, if we know it in advance, we switch on the genset, and thanks to the forecast, we save oil. This is the main message. These are some results in a thesis made in Paris. And if we have forecast, we can reduce the spinning reserve, which is a very important application. Some other results of this genset, the idea was if we have a perfect forecast, we can save a lot of. Actually, it's not now. It's not oil. It's cost. It's money. Yeah. So you can see that the skill score concerning the cost is higher when we have perfect forecast, and when we have less good forecast, but the score is inferior. Okay. So another application of short-term forecast can be done with a smart building with storage. This kind of experimentation are currently upgoing. They are very, very new. The idea is there is more and more smart building with a battery, a building which is in self-consumption. And so if there is no forecast, the rules are very easy. If it is sunny, we use the PV panel. If it is sunny but nobody is consume electricity, we load the battery. And when it is cloudy, when there is not enough electricity from PV, we use the battery and we buy electricity from the network. And if we have forecast, we can do things like if we have a sunny morning with low consumption and we know that the afternoon will be cloudy, then we can decide to load the battery. Or if the morning is cloudy and the next hour will be sunny, then we can unload the battery because the battery will be loaded in the afternoon. So we are setting up this in Polytechnique, and we will have results in a few months, I hope. And another application which does not exist really yet now is the self-consumption for houses. Self-consumption is quite easy to understand. Sorry? Okay. It's quite easy to understand. On the pink is the consumption of the house. The green is the production of a PV panel. Sorry, it was a bad button. Just for you to understand that, the surplus must be minimized. We have to do something to minimize the surplus. So all the consumption of the night can be made during the day, but it's a kind of change of life which is not easy. So here at Polytechnique, we try to use the satellite forecast to do this. Alors, to understand, at the bottom you see we draw the load of a water heater, of a dishwasher on the wash machine, and we decide that according to the forecast we can move the load of this appliance. So let's go back in the morning in 1 second, okay? We have a forecast in yellow, and then in orange we have the reality. Once we have the forecast, we can still move the program of the appliance to optimize and to give the better place on the schedule for this appliance. As you can see, the forecast was not so bad. And by moving the appliance, we could have a gain of 1.25 kilowatts, which is not big, but in a year, it's nice. Look at orange and yellow curve. This is the forecast, and as you can see, the satellite, yes, this is a mix of satellite forecast and NWP forecast, and as you can see, the satellite forecast has a better knowledge on the very next hours compared to NWP. Let's see you this third time, and it will be my last slide. So look at the orange and yellow curve. Satellite forecast a cloud coming, and orange curve said, yes, it was quite real. Okay, in conclusion, so PV power forecast at intraday scale is a very active research field. Deep learning approach have a large avenue of experimentation, and but they have to focus on reproducibility and intercomparison. Single-site forecast applications are very recent because trading electricity unit forecasts are national scale, and many forecast usages and benefits are still unknown or not yet assessed. Thank you for your attention.